Hi, this is Dr. John Bergduff. This video is entitled Transformations in Graphs, and it is meant to be sort of a summary of a study of transformations. To get to this point, hopefully you have seen a good video on some basic graphs, what I might call a library of functions. So you have a good understanding of what, for example, f of x equal x squared, f of x equal x cubed, f of x equal the square root of x, f of x equal the cube root of x, f of x equal absolute value of x. Some basic functions from which others can be built. And I hope you've also looked at some documents or some videos that explain a little bit about how changing the equation of one of these basic functions by adding or subtracting or multiplying something, what kind of transformation that would create. So with that in the background, what I'd like to do is use this as a summary. We're going to look at some functions where I've taken a basic function and added some things and subtracted some things and multiplied and so forth. And we're going to talk briefly about what the graph should look like and how you can sketch it like really fast. So with a minimum of effort, not plotting 1,000 points. So let's jump in with this one. Sketch the graph of f of x equal x plus 3 squared minus 5. Now what you want to do first is you want to have an idea of what the basic function, some people call it the parent function, looks like. That is a function from our library of functions on which this is based, a very basic function. And what I'm hoping you'll notice here is that this looks pretty much like y equal x squared. And when I talk about basic functions, I like to say, let's just know a few key points, and then we will sketch a quick graph, and we should, at this point, know what the general shape is. So by a few key points, I'm thinking let x be negative 1, 0, and 1. Plug those into y equal x squared, and that would give you 1, 0, and 1. Negative 1 squared is 1, 0 squared is 0, 1 squared is 1. And then also remember that a function of the form y equal x squared will be a parabola, and so I don't even need to draw this, but sort of in my mind somewhere, I've got a visual picture of what this graph looks like. It's a parabola passing through these 3 points, and I know it looks something like that. Not meant to be perfect, but just to give a general shape, and it is a parabola. Now, starting from there, we're going to look at what the numbers that I've added into the function will do to me. In fact, I really do want to look first at numbers that are added or subtracted, because what they will do for you is shift the graph or translate the graph. Let's take a look at the equation carefully and talk about these things. Notice that I've got a number that's been added or subtracted sort of inside the function, and a number that's been added or subtracted at the end of the function, sort of outside the function. Numbers added or subtracted inside the function result in horizontal shifts. And you might remember that they sort of go backwards from what you expect. A horizontal shift of an x plus 3 results in a horizontal shift of 3, not to the right, but to the left. A number outside the function tacked on the end represents a vertical shift. And these work more like you expect them to. Adding would make it go up, subtracting would make it go down, 5 units down. Use the origin as your key to how this transformation will move the graph. Where does the origin move to, essentially, based on the transformations you see? So if you start at the origin and you shift 3 units to the left and 5 units down, the origin reappears way over here, 3 to the left and 5 down. Then what you do with that is you next of all look and see if there's any numbers multiplied. Numbers that are multiplied have to do with stretching and translation. But we don't see any numbers like multiplied in front of or inside the function, so that doesn't apply. Then what you do is, having found the origin and realizing that there is no stretching or reflecting going on, let the other key points that you used to graph the base function or the parent function tell you how the graph will move away from the new origin. So as I look at negative 1, 1, I don't want to think of that so much as the point negative 1, 1 as moving from the origin 1 to the left and 1 up. So in similar manner, having found the new origin, there will be a second point based on that origin that will be 1 to the left and 1 up from that new origin, like that. And similarly, there will be a point that is 1 right, 1 up, based on this ordered pair. So I start at the origin again, and I go 1 right, 1 up. Notice that the shape of the parabola is beginning to take form already. And what you do is you just say from there, okay, I know my base shape is a parabola. Let me just connect these up in a nice, smooth, parabola-looking shape, like that. And that's a sketch, at least, of what that graph will look like. Very fast, very fast. I drew this also using Desmos, a computer program. And so let's take a quick look at that. The graph in red is the original function f of x equal x squared, the parent function as we call it. And then notice that the graph in blue is the actual graph that we tried to draw here, and it has indeed shifted 3 units to the left and 5 units down, but the shape of the parabola has been preserved. There's no stretching or whatever. Okay, hope that made sense. We're going to do more. Here's another one. So again, start off by thinking about the parent function. What is the function upon which this is based? And looking right here, I realize that this is based on the function f of x equal x cubed. And so whether I actually write this down or whether I just have it in my mind, I think about some key values, some key points. Notice I'm generally looking at negative 1, 0, and 1, and plugging them into this parent function. The y values would be negative 1, 0, and 1, the same values exactly. And then you may remember from looking at this before that the basic shape of a cubic function is sort of a wiggle. You go through negative 1, 0, 0, and 1, 1, which tempts you to draw a line, but we remember from drawing it more carefully that the general shape of a cubing function like that is a wiggle. So when I draw something over here on the left, it is also going to be a wiggle. It's just that some transformations will happen. So we look first into the function to see the numbers added and subtracted, because they will tell me how the graph is translated or slid. And the best thing to do is to move the origin based on what you see there. So when I look at this x minus 4 inside the function, that's telling me there's a horizontal shift, and because it's a negative and it kind of goes opposite, we are going to shift 4 to the right. And then looking at the number on the end outside the function, that's a vertical shift, and that's going to tell me that we go 3 units up. So I think about the origin ordinarily being at the origin, but I shift it 4 units to the right, 1, 2, 3, 4, and 3 units up, and I'm going to measure everything from there. Now, before I look at any of the other key points, what I need to look at next is any numbers that are multiplied. And again, where they are. I want to notice in this one that there is a -2 that's multiplied outside of the function. A number multiplied outside of the function has something to do with vertical changes, much like a number added outside the function has something to do with vertical shifts. But this would be a vertical stretch. The 2 means that we are going to vertically stretch the graph by a factor of 2. But notice that besides the 2, there's a negative. That has the effect of reflecting the graph vertically. That means reflecting it over the x-axis. Let's see how that will work. And from here, we should be able to just plot some remaining points. Now again, these other 2 key points that we looked at before, let them not so much represent the specific point, but the idea that, for example, from 0, 0, this point is 1 unit to the left of that and 1 unit down. We will move in a similar manner, but we need to take into mind the stretching and the reflecting that takes place. The stretching and reflecting is in terms of is a vertical one, so that is in terms of y. What that means then is when you would ordinarily move 1 unit to the left and 1 unit up, because we are stretching, you would move 2 units vertically, but because we're reflecting, we would go 1 left and 2 units down. Let me keep this color coordinated. So instead of 1 unit left, 1 unit, oops, sorry, I did that wrong. So let me start to say that again. So this point, -1, -1, means that we would go 1 unit to the left and 1 unit down. Because our stretch is vertical, we would go 1 to the left and we'd go 2 units, but we don't go down. Because we're reflecting, we're going to go up. Sorry about that. So ordinarily it would be 1 left, 1 down. We're looking at 1 left, 2 up because of the reflection. This point, relative to the origin, means you move 1 unit up, 1 unit right, and 1 unit up. Because we are changing it vertically, we're still going to go 1 right, but we'll go 2 units because of the 2, and because of the reflection, we'll go down instead of up. Up instead of down, down instead of up. Now those are 3 key points on the graph of my final function. And I just want to remember that although they look like they could fall in a line, because this is a cubic, we're going to get a wiggle shape, and so we draw a wiggle shape as best we can, going through those points. I might make that a little less harsh right through there. There, something like that. Hope that makes sense. Here I've drawn it on Desmos, and this is the original function y equal x cubed, and this is the transformed one. And notice that indeed it is shifted to the right 4 and up 3. It's more stretched vertically, and it is reflected over the x-axis. The red one is going up from left to right, the blue one is going down. Hope that helps. Let's look at a different function with some different things going on. Parent function. So if you look carefully at what this is based on, this looks like it's based on y equal the square root of x. Remember that we can't graph imaginary numbers, so I can't use -1 for x. I'm going to get by with just 2 points, just 0 and 1. Square root of 0, principal square root of 0 is 0, principal square root of 1 is 1. And we might remember that the general shape of a square root function looks something like this. It's a swoosh. You go through 0, 0, and 1, 1, and it just kind of swooshes off to the right. All right, let's look at all the transformations. Now, when you look inside the function and you see the plus, you might immediately be implied in thinking, oh, okay, plus means to the left. I do have to do one little thing though. I have to write this slightly differently. Underneath the radical, see that negative in there? I have to factor that negative out within the radicand still, but inside that radicand I have to factor out a -1. Actually, just a negative sign would do it. Notice that would become negative, the principal square root of a negative x minus 5. And that's important because when I look at my translation, my shifting, this is now a minus sign, and that means we're going to go 5 to the right. And this is no big problem here, 2 down. So you imagine the origin, and you say, okay, what if I shift that 5 units to the right and 2 down? That moves my origin there. But then I pay attention to numbers that are multiplied. Now, and there are 2 numbers that are multiplied. I want to point them out as I start sort of the next step. Notice that there's a number here on the outside that's multiplied. That has an effect on because it's outside the function, an effect on the verticality. Because that's 1/2, instead of being stretched, the graph is going to be vertically squished. That's a highly technical term, by the way, by 1/2. And we'll see how that works in a minute. Then there's this negative inside the radical. Quantities inside the functions have some sort of horizontal effect. If the negative were on the outside, you'd shift over the x-axis. If it's on the inside, you shift over the y-axis. So what does that mean? So if I look at my second point, I've plotted where 0, 0 goes. If I look at 1, 1, that says that ordinarily I would move 1 unit to the right and 1 unit up. But because I'm shifting over the y-axis, I won't go to the right, I'll go to the left. And because I'm vertically squished, I won't go up by 1, I'll only go up by 1/2. So I'll go 1 to the left and 1/2 up. That would put me right there. And that would give me the same swoosh shape, but it would be much more compressed. Like that. See how it's much more compressed that way. Now, little note of comment here. Unfortunately, if you're using some sort of utility to enter the graph, like in a program of some kind, these y values that are not whole numbers can be a bit of a problem. So you might have to, just for the sake of getting a graph, pick a value of x that you could plug in fairly easily, and until you get a y value that's a whole number. That may just have to be what you do. Let's take a look at this in Desmos though and see if this looks right. So I'm going to look over here. Here is my original function, square root of x. And notice in the second function in the blue, that's the one that I was going for. And it is indeed shifted to the right and by 5 and down by 2. It's reflected over the y-axis. And it is squished down vertically by a factor of 1/2. Okay, this takes some getting used to. There's a lot of art to it. It's better to think through it this way, though, than just to plot 100,000 points. Now I'd like you to try one. And before you do this, you may need to stop the video and go refresh your mind on what the parent function y equal absolute value of x looks like. You may need to look through the previous examples one more time. But what I'm going to ask you to do is, once you've done that, stop this video, try this graph on your own, and then we will work it together. So stop the video now. Okay, and we're now back. We're going to work it together and see how it goes. So we need to think of a parent function, and that would be y equal absolute value of x. That's a V shape. And to get some key points, you might remember just using sort of the same old points we always use, -1, 0, and 1. The y values would be 1, 0, and 1. and drawing just a quick sketch, or even just having it in our head, this would be a V shape going through these 3 points, sharp angle, not a nice smooth curve like a parabola. Now let's look at some of the other numbers that are involved in the transformation. Look at the numbers added or subtracted and see what they do. So I see inside the function an x minus 2. That is going to tell me that I'm going to shift 2 units to the right, because it's opposite again. And then outside the function, I see a negative 6, and that's going to tell me to go 6 units down. This tells me where my origin moves to. My origin is usually at 0, 0, but I'm going to count 2 units to the right and 6 units down, and that puts it right there at the bottom. Then I look at numbers multiplied. There are no negatives this time, so there's no reflecting over either the x-axis or the y-axis, either one. But there is a number multiplied outside the function, which is going to represent a vertical stretching, and that's going to be a vertical stretch by a factor of 3. And that tells you how the graph moves away from the origin. And here's how that goes. The negative 1, 1 would ordinarily tell you that as the graph moves 1 to the left, it would go 1 up. But because of the vertical shift, we would go 1 to the left and 3 up. And then the point 1, 1 tells you relative to the origin, you would go 1 right and 1 up. But because of the vertical stretch, we would go 1 to the right and 3 up, making a very stretched looking V shape. And you connect the points, remembering it will be a V shape, and it looks like that. How'd you do? Hope it worked out well. If not, take a look back through the video and review it one more time and try it again. Let's finish off by just looking at this in Desmos, see if this agrees. The red one again is the original function y, the parent function y equal absolute value of x. And then here is the function that we were concerned about in blue. And going back, let's just check it. It is shifted to the right 2 and down 6. You can see that. And notice how it's stretched more vertically. So I hope that helps. By the way, those of you going on to take trigonometry next semester will find all these techniques incredibly valuable when you're graphing trigonometric functions.